Hey, welcome to class meeting 23 of EECE574, the graduate level probability and random process. Still, one of the students, due to the excused absence, hasn't yet taken quiz 2, so please do not discuss on the quiz, please. Second, we have handouts and lecture videos available from the primary course webpage. Homeworks will be continue to be assigned. You can check the PLMS. There is a kind of correction or clarification due to the my hasty in the last minute of the last class meeting. I will be covering that part when I review what we learned last time. So in the last week, we started to study the equality and approximate equality of functions. First, we consider the equality of two functions. And what was the most important thing? Many of you have already forgotten. So let me review. Suppose you have a function x from some domain 1 to range 1, and another function y from domain 2 to range 2. In order to talk about the equality of these two functions, what would be the kind of obvious necessary condition? The first thing is that their domains must be the same. So domains must be the same. Otherwise, they can't be the same function. For example, as you learned in signal-gen systems, some Laplace transforms have the same functional form, but they have different domains. For example, suppose you have a Laplace transform of signal x1 of t, that is s plus a, 1 over s plus a, and s plus real part of s plus a less than or less than 0 for the reason of convergence. And Laplace transform of x of 2 having the same rational function form, but the reason of convergence is opposite, except the equality, because we can't have the equality there because s plus a in the denominator. So in this case, the function, the upper one and lower one, has the same mapping rule, apparently, in a big set, the set of complex numbers. However, their domains are differently defined. Actually, they have no intersection. In that case, we can never say two functions are the same. Similarly, in order to talk about general two functions equality, the domains must be the same, otherwise they can't be the same. So that is the first one. Second one is that, obviously, R1 and R2 must be the subset of a same or bigger function. Since R1 and R2 are not images of the functions, you can actually have different R1 and R2. However, as far as R1 and R2 are in the subsets of same big set R, then no problem. So these two are the first kind of necessary condition. And second one is this one. So since we talk about real or complex valued functions, we need to talk about which one is real, domain or range. And here, real function or complex function is the abbreviation of real valued function or complex valued function. So when we talk about x and y are real functions or real valued functions, this statement implies that R1 and R2 are subsets of the set of all real numbers. Got it? So D1 and D2 domains are not actually necessarily real. However, when I draw the graphs of x and y to illustrate some examples, I will usually assume that this D is a subset of real numbers. However, that is not required. Got it? So these are kind of necessary conditions for us to talk about the equality of two real or complex valued functions. If we talk about complex valued functions, in that case, R1 and R2, range 1 and range 2 would be the subset of complex numbers. Got it? And then we have many different definitions, not many, two definitions of equality. The first definition is everywhere equality. So x equals y everywhere. What does that mean? Everywhere on the domain. So this is defined as x of s equals y of s for all s in the domain, the common domain. And if the domain is an uncountable set, which means that the domain has uncountably infinite members or elements, then how many real value equals real value, that statement, do we need to show? Uncountably infinite. So even though this is a single line of equality, actually, we have uncountably infinite lines of equalities. In order to simply write that one using a real single equality, we may have alternate approach using set terminologies. I would not say it's set theory. So here goes the other way to write that uncountably infinite number of equalities using a single equality. That is the set of S in D such that x of S equals y of S equals the domain. Actually, they are the same statements. But here we have how many? Real value equal real value equality. In general, uncountably infinite if D is an uncountable set. However, how many equality do we have here? That's kind of strange because this equality is different from that equality, even though they have the same notation, right? When we learn the set equality, what does this mean? Actually, this means that, right? But anyway, this is a set equality equality. This is number equality equality. Got it? Anyway, another equivalent method is this one. If this is the empty set. Got it? So for every S in D, no member has inequality. Got it? So far it's kind of obvious. We can have other equalities like this is greater than or less than and less than or equal to, but that is so trivial. But here goes untrivial things like this. For every epsilon positive, as we usually state as a magic spell in the mathematical analysis, what do? We subtract and take the absolute value and consider the error, absolute error greater than epsilon. Okay. Or we may, if you want, let's start using less than or equal to first. And this one is what? This one is the same as set D. Or equivalently, for every epsilon positive, this is the empty set. Okay, got it? So it's so obvious, and though even do not feel any need to prove, but that gives us some strange thing here when we consider the convergence of sequences to a real function. Anyway, so first we define the equality everywhere, and second one is interesting. X equals y almost everywhere. on the domain D. What does this mean? In order to talk about this one, we need to introduce the notion of measure. And measure is a function here. And we are going to use a Lebesgue measure, assuming the ranges are subsets of real numbers, or we may just use a general measure defined on the kind of superset of the domains D1 and D2. Got it? But anyway, you can just assume that S is a Lebesgue measure and the domains are subsets of real numbers for convenience, but it is not always true. That is important, but anyway. So we measure the subset of D domain on which X and Y are different. And since M is a set function, which means that its argument is a set, and its output is a non-negative number. Okay, that is one of the necessary condition for a function to be a measure. Okay, so it measures the size of this set. Got it? And this size must be 0. If we want to claim that X equals Y almost everywhere on D. The reason why I do not say this seemingly same statement is not true is that sometimes the measure of domain could be infinite. In that case, that statement becomes wrong. So I'm not saying this is an equivalent definition. Got it? So this is the definition. And we have equivalent, really equivalent definitions by using many things. The first one is that suppose we integrate the difference raised to the power of P on the domain. And here P is any real number. You can choose any real number greater than or equal to 1, and if it's 0. Then you can show that this is same as that one. Of course, this measure is defined on the kind of superset of domain D. But as I told you, for convenience, you can assume that this D is a subset of real numbers, as you've seen in the homework examples. Got it? And another one is this one. Again, we use something like that. So if for every epsilon positive, now this almost everywhere equality is related to the measure. We are going to use not only for every epsilon positive, we measure the set. And here, the subset of D such that X of S minus Y of S. And here, similar to the, where it is? This one or that one, but here we do not use equality. So what do you want? So what we do is that we take greater than epsilon, and this tends to 0. Okay. Just a sec. I'm sorry, not yet. No, no convergence. I'm sorry. This equals 0. Okay. Yeah, similar to this. Got it? So for every epsilon positive, if the measure of this set is 0, then you may say that X and Y are equal almost everywhere. Okay, so far so good. Yeah. So this part is done. Now let's consider a sequence of functions. So we have X sub n of S, if you want, and n from 1 to infinity. And we have the limit or the target of the limit. sometimes I say X, sometimes Y. So it depends on the context. But we have something similar to the equality and almost everywhere, everywhere equality and almost everywhere equality of two functions, something similar. But there are also some different definitions. The first one is the uniform convergence. Where it is? Okay, just a second. Okay, yeah, I know why this is complex. So I was reviewing that. Yeah, so I was talking about that part. Okay. Yeah, sorry about that. So now we consider general convergence of a sequence of real functions. Okay. The first one is uniform convergence. And what is uniform convergence? Uniform convergence is very simple. You start from the limit function. So if your target is y, or if your target is x, what you do is that, so suppose this is x of s, then what you do is that for every epsilon positive, you find a band that is epsilon greater than the x of s and epsilon less than x of s. So this becomes x of s plus epsilon and x of s minus epsilon. And what you want is that for sufficiently large n, your x of n is inside this for every n. Okay. After some point, for every n, your x of n resides in this band. Ready? In that case, here uniform means for all s, you select single epsilon. Ready? And second one is everywhere convergence. And this is related to the point of view where you consider a function evaluated as some number, s. You have a sequence of real numbers. So suppose this is the sequence of functions, but you choose some specific s0. Then what do you have now? Given specific s0, you have a sequence of real numbers if xn is a real valued function. And now you consider, you check whether this sequence of real numbers converges to x of s0. So convergence everywhere is related to, just a second, let me have some space. Okay. So xn converges to x almost everywhere, of course, on the same domain. Otherwise, you cannot say that. If what? Almost everywhere is always related to the measure of some function, right? And also, whenever you talk about a sequence of something converges, you may want to start for every epsilon, blah, blah, blah. But here, it's not related to the for every epsilon, but still, but you love this measure. So you measure the subset of D where xn does not converge to x. And if this set has measure 0, then you say that xn converges to x almost everywhere. Then what about everywhere? Xn converges to x everywhere. If without measuring, okay, you just say that the subset of D on which xn does not converge to X is the empty set. You see the difference? Here, this set is not necessarily an empty set. It just needs to be its measure 0. Got it? So the example is that, for example, suppose you have some function where it converges, so say D is this closed interval 0, 1, and your xn converges to X for S in 0 and 1, but does not converge to X for S 0 and 1, which means that at the end points, they do not converge, but otherwise they all converge. Now, suppose this set is that one. What is the length of the set that includes 0 and 1 only? It's 0, okay? So this is everywhere convergence. This is almost everywhere convergence. You clearly see that you have measure of the set equals 0. So here you have equality. This equality is the equality between two real numbers, right? Right side is 0. That is a real number. Left side is the what? Is the mapping of this set to a real number. So this is real number. But here, this equality is the set equality. And this subset is empty. That means you have everywhere convergence. Now, so this is the first one, uniform convergence. And this is everywhere convergence. And this is almost everywhere convergence. Now, unlike the equality of two functions, these two definitions modified allows us to define this convergence in a different way. So first one is this one. Xn converges to X in the pth mean. Here p can be any real number greater than or equal to 1. And if, so again, you integrate the difference between the nth function and the limit function raised to the power of p on the domain. And let me ask you, what is this one? Is this a number? Yeah, it's a number, but it's parameterized by n. So actually, here you have just defined the sequence of real numbers, right? Non-negative real numbers. So you have a sequence. What do you want to say? It converges to 0 as n tends to infinity, which means that for sufficiently large n, this integral is very small. Then you say that xn converges to X in the pth mean. The most famous of them is the case when p is 2. In that case, we say that xn converges to X in the mean square sense, or the convergence is in the second mean. Got it? And the last one is the convergence in measure. And this one, at the first glance, looks very similar to the almost everywhere convergence. However, we have a difference. So we start from this measure. So we have some measure. And this measure is a set function. So we want to plug in some set as the argument. What kind of set? Of course, it's a subset of D. And what do you want to do? Motivated by that one, you may want to put the condition where the difference between here x sub n and x, right? The nth function and the limit function greater than epsilon. Now, let me ask you a question. What is this one? This is a number. It's a real number, okay? And in general, in our case, if we use Lebesgue measure or something, this is a non-negative real number. But it's parameterized by what? N and epsilon. For example, suppose you fix epsilon to 10 to the negative 5. Then if you change n, you have a different number. So you have some sequence, let's say y sub n of epsilon. And what do you want to say? First, suppose xn is very close to x for sufficiently large n. What does that mean? This set, the difference is greater than epsilon, would be very, very small. So this measure will be very close to 0, which means that you may want to say that this converges to 0. But still, you have epsilon. And what do you want to say? For every epsilon positive. Okay. So how many convergences of sequences of real numbers do you need to prove? Actually, uncountably infinite. Because whenever you choose epsilon, whenever you change epsilon, you have a different sequence. And for each sequence, you must show the convergence to 0. Got it? Anyway, so if you compare these definitions of 5 convergence of sequences of real functions, they look similar, but you can find they are different. And I'm not going to prove, but we can show this. This is the relation between these 5 different definitions of convergence of a sequence of real functions. If a sequence of functions converges uniformly, it converges everywhere. If it converges everywhere, it converges almost everywhere. So uniform convergence, everywhere convergence, almost everywhere convergence. So these first 3 definitions have this relation. What does that mean? So here, the point marked x is what? Represents a sequence of real functions, right? Even though I have a single point in this set, that consists of a sequence of real functions. And if x is inside its uniformly convergent sequence set, then it is also in the every convergent set and is also in the almost every convergent set. What about this element marked by triangle? This also represents a sequence of real functions. This converges everywhere, but it's not necessarily converging uniformly. What is an example? You already know. Given a discontinuous rectangular wave, you derive a Fourier series. With that Fourier series, you find the Fourier series representation consisting of countably infinite number of sines and cosines. You can easily show that, that is there. Okay, this is square wave. And Fourier series. Okay, I'm sorry. So if you truncate the Fourier series up to nth term, then you have a sequence of functions. That sequence of functions converges for every continuous point of this scale wave. However, for the discontinuous points, it converges to the center, as you remember. So this example resides here. It's not converging everywhere. It's not converging uniformly. Okay. And also, you know that there is Gibbs phenomenon. So actually, you have a peak that is not reducing. Okay. One good thing is that the energy of that one converges to 0. So here you can easily show that this is what in the second mean, something like that. So this convergence in the fifth mean, among these many, actually this is a single one, but actually there are many, right? As you've seen in the example in the homework, some sequence of functions converges in the second mean, however, it does not converge in the third mean, something like that. Anyway, so this example, square wave as a limit function and the truncated Fourier series representation as a sequence of functions is almost everywhere converging, and also it converges in the second mean because the error converges to 0. Okay, yeah, something like that. And finally, you have a convergence in measure. That is very interesting. And that kind of is here. So these imply convergence in measure, and these imply convergence in measure. Got it? That is the review. So what I wanted to clarify here is this one. Convergence in measure requires convergences of uncountably infinite number of sequences parameterized by epsilon. Because for every epsilon positive, you construct a sequence of real numbers. And each sequence converges to 0 as n tends to infinity. So you have how many? Uncountably infinite number of sequences. Now, let's start our discussion on the sequence of random variables. That is the main topic. Actually, in order to learn this one, we've reviewed, or not reviewed because you didn't take the measure theory. But anyway, we reviewed the equality of two real numbers, approximate equality of two real numbers by using sequence of real numbers. And we've reviewed the equality of two real functions and approximate equality of two real functions, blah, blah, blah. Okay. Now, let's go back to our friendly old figure. Suppose here is a random number generator or random event generator or random experiment. So you have an outcome that is S. And here, this entire property of the random event generator or random sample generator is governed by, described by the probability space consisting of the sample space and the event space and the probability measure. Got it? And what is a sequence of random variables? Basically, a random variable is a function, right? So when you have a sequence of random variables, it's similar for you to have a sequence of real functions. So convergence of a sequence of real random variables has very similar property to the convergence of a sequence of real functions. The most important difference is that in probability theory, our measure is the probability measure, and the probability measure is always generating a value less than or equal to 1 because we define the probability measure in that way. The empty set is probability measure 0. The entire sample space has probability measure 1, right? And then we have countable additivity, blah, blah, blah. So there is a difference. Now, we also define the same 5 modes of convergences like this for the random variables. However, as I just told you, the main difference in probability is that we only deal with some quantity through probability measure. So probability measure is very important. So definitions that does not involve the probability measure has no meaning, actually. What does that mean? Consider equality of two random variables first, okay? As we've done here in the equality of two functions. So just for simplicity, consider two random variables. Definitions. Two real random variables, x and y, are equal. What does that mean? What should it mean? Are equal. Whenever you handle random variable, remember that without probability measure, almost nothing has meaning. Okay? So you start from this probability measure and want to say something. What? Probability measure admits, because it's a set function, it admits an event. That is a set. So here you must put an event. What kind of event do you want to put? You may want to put the event x equals y, or you may want to put the event x not equal to y. And you may say, oh, what was the definition of this one? I do not remember. Then, in that case, let me revise this one using a more set theory-like notation. So you consider the subset of the sample space on which x of s equals y of s. Oh, okay. Now it's more similar to you've just seen in the equality of two real functions, right? So what is this one? Subset of S on which the function x and the function y has the same value. And if this set has probability 1, right? Then you want to say they are equal, but with probability 1, with probability 1. Okay? So this is important. Okay? Everywhere equality doesn't mean much when you deal with probability or random variable. So this is the most important definition, but with probability 1 is similar to what? The almost everywhere equality when we just dealt with general functions. So it is often called equal, almost. But here, since we only consider the probability measure, we say almost surely. Sometimes people say two random variables are equal almost everywhere. But actually they meant what? Almost surely, or with probability 1. Okay? Then equivalently, you can use inequality and the probability equals 0. Okay? So they are the same. So equal, almost surely. And what would be the equivalent definition? Because this almost sure equality is mathematically same as the almost everywhere equality for two real functions. What can you say? Amazingly, what? You have the same thing. So if this integral is 0, this statement is same as that one. But when we have, I'm sorry, there is type, so not SPS. Probability measure, okay? What is this one? Value times probability. So it's expectation. So this is same as expectation of x minus y raised to the power of p equals 0. Got it? For p greater than or equal to 1. So simply by showing some expectation is 0, you can easily prove they are almost surely equal, or they are equal with probability 1. When you have two real random variables, yet we haven't yet started to discuss the sequence of real random variables. Not yet, okay? And another one is this one. We can also use for every epsilon that magic spell. What would be that? Again, the probability measure of the set of sample space such that x and y differ greater than epsilon. That is 0 for all epsilon. They are all the same. But probably this would be the simplest way to show two random variables are equal everywhere, almost everywhere. Okay? So this is the one. But now let's consider sequence of random variables. And the first one would be the convergence in almost everywhere. What would be that? Convergence almost everywhere. So in order to define convergence in almost everywhere sense, here goes the definition. So this is equality. Okay, these are what I've just told you, right? Equality of two real random variables. First, almost sure, right? They are same. This is also the same, okay? By the way, I forgot to talk about this one. Two random variables are equal in distribution. What does that mean? Their CDFs are the same, okay? The problem is that even though CDFs are same, they are not necessarily the same random variable. For example, suppose x is a uniform random variable having the density function like this. Okay, you know it's a uniform random variable. Now let's define y as 1 minus x. Then what's the difference between the CDF or PDF? No difference, right? However, if you plot a scatter plot, this is realization of x and that is realization of y, then what do you have? You always have dots on this line where x plus y equals 1. What does that mean? This is the line for x equal y. So in this case, probability of event that x equals y is actually 0. They are not equal at all because the probability is 0. Got it? However, their CDF or PDFs are the same. In that case, you can say that they are same in distribution, but not in this case almost surely, or they are not equal with probability 1. Got it? However, you can easily show that if x equals y almost surely, their CDFs are the same. Got it? Okay. Yeah. Here goes the definitions. The first one. The sequence of random variables converges to another random variable. And this is obvious because a random variable is a function and its limit must be a function too, right? So xn converges to a random variable in general. It could converge to a very special random variable, which is constant with probability 1. However, a constant is also a special case of random variable. So whenever you talk about a convergence of a sequence of random variables, you should consider the limit as a random variable. Anyway, the first definition, xn converges to x almost surely. What does that mean? You take the set on which xn does not converge to x, and you calculate the size of it. That is this one. So you compute the probability of the event that they are the same. Or if you want, it converges or it does not converge. So this is same as this statement. Okay? So you collect every S where the random variable converges, and its measure must be 1. Equivalently, you take the S on which xn does not converge to S. Its measure must be 0. That is the almost everywhere convergence, or with probability 1, with probability 1 convergence. Because you talk about with probability 1, okay? So when you say probability 1, you must take this one. However, they are equivalent. Now, second one is the convergence in the p-th mean. And to talk about p-th mean, you just simply calculate the expectation of the difference raised to the power of p. And as you know, what is this one? This is a real number parameterized by only n. Suppose p is fixed. Then you have a sequence of real numbers that converge to 0, right? For that specific p. Then you say that the sequence xn converges to x in the p-th mean. If p equals 2, it converges in the mean square sense. And you have some notation. What? xn, you take the limit in the mean. Okay, so limit, sorry. Limit in the mean xn equals x intensity. This is the notation for the convergence in the second mean, or convergence in the mean square sense. What does that mean? Expectation of xn minus x raised to power p, power of 2, converges to 0 for n as n tends to infinity. So you compute the expectation, and that sequence converges to 0. And here goes the third definition, convergence in probability measure. So it's related to the convergence in measure for the sequence of real functions. What do we do? For every epsilon positive, you construct, for each epsilon, you construct a sequence of real numbers that converge to 0. In order to do that, you take the probability measure of a set that becomes smaller and smaller. So here, you take the probability of the event. That event has smaller and smaller size as n tends to infinity. So you take the absolute value, the difference greater than epsilon, and that converges to 0 for each epsilon positive. If that holds, you say that the sequence of real numbers converges in probability measure, okay? But we usually say in probability. Now, finally, we have convergence in distribution. As we've seen in the equality of two real random variables in distribution, we are interested in the CDF only, okay? So given a sequence of random variables, xn, you compute the sequence of CDFs, okay? And that converges to the CDF of the limit random variable. But this is what? This is actually related to the convergence of a sequence of functions to another function, right? So we know that there are 5 modes of convergences. Which one? And this says that it's kind of similar to the almost sure convergence. So you take every x. For every x, point-wise, at each point, this function converges to that one, except discontinuous points. Okay, so in some points of uncontinuous, so CDF can be discontinuous, as you know, right? CDF could be discontinuous if there is a point mass. So except those points, the sequence of CDFs converges pointwise. By the way, there is a theorem that's equivalent to this definition. And this is very useful. That is what? The limit of the characteristic function of x of n equals the characteristic function of x of omega. Of course, for all omega. But since the characteristic function itself is an integration, because this is defined as the expectation of e to the j omega xn, right? And this is defined as expectation of e to the j omega x, right? At some point with measure zero, they could be different. It doesn't matter. So here equality is more related to what? The equality in the equivalence class. Okay. Anyway, so there are 4 important modes of or definitions of convergence of sequence of random variables. Here, everywhere convergence is not that important because anyway, we need to involve the probability measure. You see, here, what is CDF? Probability of some event. What is this one? Probability of event. What is this one? This is also related to the integration of something dp of s, right? So it involves the probability measure. It also involves probability measure. So the convergence definitions for the general sequence of real functions are not important unless it involves the measure. So we just forget about uniform convergence. We forget about everywhere convergence. We're only interested in convergence with probability 1, convergence in the piece mean, convergence in probability measure, and convergence in distribution. And their relations are also plotted like this. Almost sure convergence implies in probability convergence. In the piece mean convergence implies in probability convergence. In distribution, it's implied by all the others. So if you want, you may draw like this, almost sure convergence. Some, let's say second mean, okay? There could be some sequence of random variables that converges almost surely and in the second mean. But some sequences of random variables converge almost surely, but not in the second mean. Some converges in the second mean, but not almost surely, as you have seen the homework examples. And these are all included in convergence in this in probability. And they are all included in the convergence in distribution. Of course, given any sequence of random variables, this set of the convergent sequences of random variables would be very, 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 very small, right? In general, they could not converge, but let me just exaggerate the size. So it's the set of all sequences of random variables. Okay, let me repeat. This set is very small, almost invisible. I just exaggerate. Okay, but anyway, these have relation like that. Got it? And not just the definitions, but let's see some examples. Okay. And what is interesting is the law of large numbers. Okay. And this is an example of some almost sure convergence or in probability convergence. So let's see. You've seen the term, the law of large numbers. Actually, there are laws of large numbers. So there is no single the law of large numbers. This is wrong, actually. There are the laws of large numbers. So suppose that here is the set of all. I really love the set of all law of large numbers. Okay. And first thing we want to study is a strong law. By the way, there are many versions of strong law of large numbers. The commonality is that their convergence. They talk about convergence. So strong law of large numbers. Strong law of large numbers. So this is a kind of law of large numbers. And here you have a subset of strong law of large numbers. And of course, there are many different versions. But the first one is, for example, the commonality. Commonality of this one is that they all talk about almost sure convergence. Okay. And there is a weak law of large numbers. And let's say that all the others, not all the others. Let me just say weak law of large numbers. Okay. And weak law of large numbers is related to the convergence in probability. In that sense, the law of large numbers can be different. Okay? For example, this one, to prove some theorem, this mark X means a theorem. Okay, here is a theorem. And the commonality of law of large numbers is this one. And actually, there are many versions of so-called commonality of large numbers, but the simplest one is this one. Suppose you have anyway, you have definition. Given a sequence xn of real random variables. And we assume very simple thing. Usually we assume xn's having the same mean. Okay. And here goes some conditions. Sometimes that condition says the variance of xn is the same. Sometimes they even do not talk about variance. So depending on this condition, you have different strong law of large numbers. But the commonality is this one. What you do is that you construct mu sub, let me say, n. Okay, that is defined as the arithmetic mean of first n random variables. Okay, so given a sequence itself does not converge. You construct a new sequence. See that? These are random variables, jointly distributed. So actually, mu sub n, let me see m sub n. Okay, mean. Okay, so let me use capital M. Okay, m sub n. Because if you change n, you have different m sub n, right? So you construct a new sequence of random variables. And now, strong law or weak law or any law of large numbers means that xn converges to mu in some sense. Then you say that we have a law of large numbers. If this sense is almost sure sense, it's a strong law of large numbers. If this sense or mode of convergence is in probability, then it's a weak law of large numbers. Got it? So there could be many different law of large numbers depending on this condition, and there could be many different law of large numbers depending on that condition. Okay. Among many law of large numbers, actually in probability and statistics, or in probability and random variables undergraduate course, or in other graduate course, you've learned very specific, in general, very simple in most of cases, very simple or simplest theorems named as the strong or weak law of large numbers. And let's see some examples here. Okay, where is? Yeah, here goes one theorem, a strong law of large number. Okay. And this strong law of large number has a very good, very simple property, or among x of n or x of I. Okay. So anyway, the index could be n or I, no problem, right? You have a sequence of real random variables that are independent and identically distributed. Very, very strong condition. Okay. So here, as I just told you, this condition is not necessarily IID, but in that theorem, this line has what? IID needs of random variables. And also, it has one more thing. Of course, same mean. Otherwise, it does not make sense. But of course, IID means that they have same mean, right? But sometimes you must be careful. Some random variables does not have the mean well defined. But in this case, we assume the sequence of random variables has the finite mean defined. And also, since they are IID, variance could be non-existent or existent. If they are existent, they must be the same. Here, it is assumed that the variance is finite, exists and finite. Okay, so assumption is that IID with a finite variance. By the way, if you take some little bit advanced probability theory, usually the course says that if you want to say that the variance of a random variable exists, it is necessary for you to have its mean finite, existent and finite. So actually, this IID with a finite variance means that they have well-defined mean. So this line replaces this line in that theory. Got it? Now, what kind of convergence do we have? Since it's a strong law, here, you see, we construct a new sequence, mean sequence, taking first n of the random variables and computing the arithmetic mean, right? This converges to the common mean with probability 1. Or you may say that almost surely. This is the strong law, a strong law. Okay? There could be different strong laws. Be careful. This is not the unique, this is not the only strong law of large numbers. There are many, 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 many versions. Even when I was a graduate student, my colleague in the math department was proving new law of large numbers under different conditions. Okay? So there are many different versions of strong law of large numbers, but there are some famous like this. Okay? Proof is omitted, and you can prove that one by using different. But anyway, the second one, a weak law of large numbers. And here, again, you have a sequence of real random variables. But what condition? Here, pairwise uncorrelatedness. What does that mean? If you take only 2 of them among countably infinite random variables, you take just 2. You take just 2 and 2. Then they are uncorrelated and having the same mean in this case. Okay. Of course, this line could be different in other version of a weak law of large numbers. So same mean, but uncorrelated, and same variance existing and finite. Okay. You see the implication? If this is true, that is also true, right? If sequence of random variables are the random variables are IID and having same mean and finite variance, then this is also true, right? But anyway, this is weaker condition, much weaker condition. And the arithmetic mean sequence converges to the common mean now in probability, which means that in probability measure means it's a weak law of large numbers. Okay, so let me repeat. Every law of large numbers somehow involves the sequence of arithmetic mean of random variables. And they usually want to show that that arithmetic mean of random variables converges to a common mean. Okay? But under different conditions and also under different mode of convergence. In that sense, there are many different versions of law of large numbers, but you can classify them into mostly two if you want. And if you want some new convergence, you can define kind of strong, some law of large numbers in the second mean. You may say that, but anyway, strong law proves almost sure convergence. Weak law proves in probability convergence. Got it? And let me remind you, if a sequence converges almost surely, it converges in probability. So if you have proved a strong law, it automatically proves a weak law. Got it? And there is something related to the convergence of a sequence of real random variables. That is the central limit theorem. The central limit theorem is one of the most well-known convergence results. However, most misunderstood convergence. So probably I have enough time. So here goes the central limit theorem. And there are also many different central limit theorems. So here, this is the set of all central limit theorems, let me say, okay? Suppose you have many different versions of central limit theorem. What would be the commonality? What would be then the difference? The commonality is this. Any central limit theorem is related to what? Something converges to so-called Gaussian distribution. Okay? So commonality is that a sequence of real random variables converges to a Gaussian. Then what? Gaussian random variable. So here goes a very different property of CRT. In the law of large numbers, what was the limit? Number. Even though it's a special random variable, it's a number, right? See that? This is a random variable, a constant random variable, right? Be careful. This is a constant random variable. But in CRT, it converges to a non-constant random variable, a Gaussian distribution. Got it? So that's the difference. In the law of large numbers, be careful. It converges because it's a sequence of random variables. It converges to a random variable. However, that random variable is a constant random variable. But in central limit theorem, it converges to a Gaussian random variable, not a constant. Okay? And usually, it's not always. Usually, we show that some sequence converges to a standard Gaussian random variable. But there are many different standard Gaussian random variables. And you may say, what? Standard Gaussian random variables are all the same. No, it's not. Be careful. Suppose X is a standard normal Gaussian. And as you know that, minus X is also a standard Gaussian, right? But they are not the same, right? So even though we show a sequence of real random variables converge to a standard Gaussian, we need to be more specific. What? The convergence is in distribution. So we show that given we construct a sequence of real random variables that converges to a standard Gaussian in distribution. What does that mean? Suppose our constructed sequence is G sub n. Then what we show is this. The sequence of CDFs of G sub n converges to the CDF of standard Gaussian. Or equivalently, the CDF sequence of CDFs of G sub n converges to the CDF the characteristic function, okay, CF. Okay, here this is CDF and this is characteristic function, CF of the standard normal. By the way, what is the characteristic function of the standard normal? E to the negative omega square over 2, right? So you need to show that the sequence of characteristic functions converge to this function. Very simple bell curve. And here, what was that one? This requires the integration, right? You know that the CDF does not have a closed form, right? So we are going to see more on this Thursday, but be careful. The central limit theorem usually shows and usually construct a sequence of random variables that converges to a standard normal in distribution. Got it? If you have non-standard normal, define a new sequence that converges to a standard normal, and then prove the convergence in distribution, and then rescale in order to show that your sequence converges to, for example, some non-zero mean and some non-unity variance. But to prove and claim your theorem is a central limit theorem, prove this one. Got it? Okay. Let me finish here and continue on this Thursday.